So in front of you, you will find the agenda for today's seminar. And in a few minutes, I will pass an attendance sheet. And I'll be pleased if you can just fill your name, organization, and email just to reach to you easier in the future. So to make it short, please help me to welcome Dr. Marwa Hassan, the Director of the Tran-SET UTC.
Thank you. Thank you, Mohammed. Good afternoon, everyone. I hope you're having a good day. My name is Dr. Marwa Hassan. I'm serving as the Director of Tran-SET right now. We are lucky to have Dr. Hatem speaking for us today. But before I give him the mic so that he can start his talk, I'm just going to give you an overview of what Tran-SET is. Some of you know, some of you don't know, right? So what is Tran-SET?
It's the wrong.
All right. So as I said, I'm the Director of Tran-SET, and in Tran-SET we are trying to solve emerging transportation resiliency, sustainability, and economic challenges through the use of innovative materials and construction methods. And we focus on the whole life cycle of the research. So we don't just do research, but we try to take it from research all the way to implementation, as much as possible. So what is Tran-SET? Tran-SET is a university transportation center. Every 3 to 5 years, the US DOT administers a competition. This competition is for the formation of transportation centers. They fund 5 national centers, 10 regional centers, and 20 tier 1 centers. The levels of funding decrease from one category to the other. If you look at this map right here, you will see that they divide the US into 10 regions. Hence, each region gets 1 regional center. Our Tran-SET is the regional center representing Region 6, which works with 5 different states: Louisiana, Texas, Oklahoma, New Mexico, and Arkansas. So I sometimes joke about this, but we are leading Texas, so that's good, right? We got our funding in November of 2016, so this is our 3rd year of work cycle. We have 11 partnering institutions, 9 universities, and 2 community colleges. You can see a list of all the universities right here, and you can see that we have Texas A&M among them. We have University of New Mexico. We have Oklahoma State, Arkansas State. But we also have 2 community colleges, one right here in Baton Rouge, which is BRCC, and the other one is a tribal community college called Navajo Technical University. And we have a summer program where we invite people or students from NTU to come here and work on research projects at LSU so we can teach them and do cultural/technology transfer. Okay, so as I said, our vision is to address the accelerated deterioration of the transportation infrastructure. How do we do that? We develop, evaluate, and implement cutting-edge technologies, use new materials, and try to implement innovative construction management processes. And we look at all phases of research: tech transfer, workforce development, and outreach to solve any regional transportation challenges that Region 6 is facing. So just to give you a quick overview, we are mainly concerned with improving durability and extending the service life of the transportation infrastructure. But because we are a regional center, we also fund projects in preserving the environment, in preserving the existing transportation system, and anything else that would be a regional priority. And I'm going to talk about this a little bit in a minute. Before I do, the objectives of the centers is to enhance durability by the use of innovative materials and construction methods, promote sustainability and resiliency, look for cost-effective solutions for the project backlog that's present, especially in Louisiana, look for cost-effective solutions for maintenance of the infrastructure, enhance resiliency, especially under hazardous conditions, because we are susceptible to a lot of hurricanes and so on, and promote workforce development and education in transportation. This is kind of what we are all about, but I'm going to give you a snapshot of what we've done to date. So we've had 2 cycles, and we are in the 3rd cycle right now. In the first year, we funded 33 projects for $4.4 million. $363,000 of that came from external match from companies, agencies, and so on. And we created 8 private-public partnerships. had collaborative projects between different institutions. We had 11 multi-institution projects, and we were able to support 99 students between graduate and undergraduate. From a regional priority, these are the areas that we're focused on under regional priority. So we look at projects that enhance metropolitan growth and congestion, future transportation challenges, declining public revenues, underrepresented communities, and safety. And we, as you can see, with respect to transportation, we fund projects in many different areas: asphalt materials, concrete materials, pavement, geotechnical, structural, ITS, policy planning, and so on. So it's a very diverse portfolio of funding. Of course, we want all our data to be available to everyone. So everything is posted on our website, and our website is called Tran-SET.lsu.edu. We also save everything on the LSU Digital Commons, so not just the final reports of the project, but all the data sets that were generated. In that case, if you are a student working on a related research project, or a researcher that wants to pick up the research, you can actually download the data and use this data to generate more work from it, papers, etc. And everything is available on the LSU Digital Commons website. The second cycle was similar to the first. We funded 33 projects for $4.4 million. We increased the external funding. It went up to over $580,000. And we kept the public-private partnerships and supported 80 students. If you look at the project portfolio here, this just summarizes the distribution per research area and with respect to regional priorities as well. The third cycle project just started August 16th, so we have funded all the project and people started working. We received 74 problem statements. We funded 35 of these problem statements. The total funding for year 3 is $4.8 million, and we increased the external match again to $713,000. So we're growing slowly and increasing our partnerships throughout the region and the US. We increased our public-private partnerships to 17, and we still have collaborative projects, 8 of them this year. This is the distribution of what Year 3 is going to be. Similar to Year 1, all the data from Year 2 projects is also available for download in digital commons. In addition to research, we have a strong focus on education, outreach, workforce development. So just to give you snapshots, 6 of our 11 institutions are minority-serving institutions, so we have a strong push on diversity. We hire both undergraduate and graduate students. If you're interested in transportation-related research, come talk to me. Even if you don't want to work for the whole year, if you want to get a perspective, you can work for a semester or over the summer in some of the projects. We develop a lot of educational modules that are integrated within the current courses at LSU and other universities. We also revise existing courses, and we host different events, and they vary from one time to the other. So this is an example of the Summer Transportation Institute that's hosted in University of New Mexico. We work with existing programs at LSU, like Excite, for example, to give an experience to the students at LSU. And we publish a quarterly newsletter, thanks to Chris Melson sitting here. It comes out on time every time, so we appreciate it, Chris. Workforce development and tech transfer, we have a number of programs. Again, I'm just giving you some snapshots. The Veteran Scholarship Program is one that's close to my heart. And what we have done is we have partnered with the Construction Education Trust Fund and EGC, and they have matched the dollars that we're putting from Tran-SET 1-to-1. So we have scholarships that's available to active military and veterans that can allow them to get an advanced degree in transportation, so they can get a master's degree, fully covered tuition, and they get about $25,000 of scholarship. We host an annual conference, so next year it's going to be in Albuquerque, New Mexico, if you guys want to come. We also participate in different conferences. That's an example of one, ICTIC. In this particular year, we had a Tran-SET track in China in the World Transport Convention. We develop a lot of seminars and workshops, and now we are, I'll jump down and then come back. We are trying to do this on a regular basis, so the seminar series is going to be monthly from now on, and Dr. Hatem, thank you for being the first speaker that we host at LSU. With that, I thank everyone for being here, and just give the floor to Dr. Hatem so that he can talk to us.
So before introducing introducing Dr. Hatem, I would like to thank him for his flexibility to organize this seminar. So Dr. Hatem has 20 years of experience in structural engineering with special emphasis on design and behavior of reinforced and pre-stressed concrete structures and bridges. In addition, he has an extensive experience in finite element analysis of structures and bridges. Further, he has vast experience in retrofitting and rehabilitation of structures using fiber reinforced polymers as well as traditional techniques. Dr. Salim is a member of the Transportation Research Board Standing Committee of Structural Fiber Reinforced Polymers and served as council member of the International Institute of FRP in Construction. He's an associate member of ACI Committee, Bridge Design and Design Offshore and Marine Structure. Dr. Salim is a recipient of the 2014 American Concrete Institute Chester Hall Award for Excellence in Structural Research. In addition, he's a member of the standing committees of Egyptian Code of Practice for Bridge Design and the Egyptian Code of Practice for Rehabilitation of Structures using FRP. So please help me to welcome Dr. Hatem.
You can change the presentation.
Good afternoon, everybody. First, I would like to thank Dr. Hassan for giving me the opportunity to be here today with you. And I'm really impressed with the introduction that you made about the Tran-SET.
Thank you.
I didn't know about all these activities that you have been doing for the past 3 years. And I'm really privileged to be here with you today at LSU. So today I'm going to talk about enhancing the live load carrying capacity of infrastructures, which you always think that's mainly bridges, but it does apply for sure for other structures for extended lifespan. So the outline of the presentation we're going to talk about. To do that, we typically we all know about the use of FRP in civil and structural engineering, and that's the fiber reinforced polymer materials. But what I would like to highlight today, that's not only the use of the material by itself, it's a combination of the use of the material, how you have the good engineering understanding, what are the engineering tools, and what other type of tools you would need to do a full assessment of your structure to end up with an efficient long-term solution for your structure. So first, definitely I'll start talking about FRP materials and introducing the type of the FRP materials that we use in our structure engineering application mainly. Fiber reinforced polymers, so we expect fibers. And mainly we have the 3 types of fibers, the glass, carbon, and aramid fibers, and those are the 3 most common fibers that we use in our structure or civil engineering applications mainly. There are some other types of fibers like the basalt fibers that start to make their ways into concrete applications, but still the most widely used, at least in structure application, is mainly the glass fiber, and the carbon fiber is also used, but for external application, we mainly look into glass. So we have a fiber and we have a resin. That's why it's called a composite material. We have a fiber and a resin. Based on the type of fiber you are using, you'll end up with a glass FRP, carbon FRP, or aramid FRP. Basic understanding of the material behavior, we know yes, fibers are very strong, but we cannot use the fibers individually. We have to put them in a matrix, which is typically our resin, to have a composite material. So the fibers are very strong with very high tensile strength, very high modulus. Your matrix is the one that has the lower modulus. It's much weaker. You end up with the FRP composite system, and that's the average or in between the both. Even nowadays in our structure design, we have a tendency now, or the code, the ACI at least guidelines, requires the use of the composite material properties. It was acceptable before to use the dry fiber properties in your design. Nowadays, we switched completely to the use of the composite material properties. And yes, it does make some difference. Just to give you an idea, the strength of the FRP versus conventional reinforcing steel bar. So yes, they are higher strength than steel, for sure. If you look at the carbon, you will notice that, sure, I didn't have a laser pointer, so I'll try to use the mouse here. The glass, they are higher strength, but they have a slightly lower modulus of elasticity than steel. Aramid is better than glass, slightly less than steel. With carbon, you are getting close to steel. You even can have high modulus carbon, and the high modulus carbon, they can even have a modulus of elasticity much higher than the conventional steel bars. And those are mainly intended for the use for the strengthening or the rehabilitation of steel structures. Because for steel structures, you cannot use a material that has a lower modulus of elasticity than your original steel beam. For concrete, that's not the case because the concrete has a lower modulus compared to steel. Still, the carbon fiber is the most widely used. We are looking into strength at least 5 times that of the steel if we are looking into carbon. So mainly we are looking the average, the high strength to weight ratio, if we're looking into carbon fibers to steel, we're looking into the range of 30. Material and durability, that's always the question, that when you start talking about new materials in general, either FRP or any other type of materials, it's always the question, is the durability? Yes. As civil engineers, we have to deal with the structures that have to be designed for a lifespan of 75 years, sometimes maybe even 100 years if you are talking about special structures. Conventionally, any structure will be at least for 50 years. So we have to have materials and structure that are required to last for that long. Unfortunately, we don't make cell phones that will last for a year or two. We have to make a structure that will stand for 75 years with the same acceptable level of performance. So durability is always the question. Yes, we do address durability. And this starts from the early stage even in design. When we start designing our material, even the FRP, we account for this by accounting for the type of the exposure, the type of the structures, and they use a lot of reduction factors, even in our design that reduces the material strength to account for the durability. In addition, we have projects and structures that have been prepared. Oh, thank you so much. Sure. The screen. Okay. So, thank you so much. And also the other advantages of the material, it's a non-magnetic, non-corrosive, and that's what makes the FRP is a very appealing option for rehabilitation because it does not corrode. So it's not prone to corrosion like steel. It's a very low profile. We are talking about the thickness. It's millimeters or fractions of an inch. So when you actually repair a structure with the FRP, it's not like adding a steel plate or enlarging your concrete member or encasing. You are looking about a very low profile. And it's fast and easy application. So in terms when you are doing damaged structures, you need just a matter of hours or days to repair your structures. Common types of FRP, yes. We have the wet layup system, which is basically the sheets. We also have the other products like the laminates or the plates, which is still used. Sheets are more common to be used. It all depends on the type of the application and the design. So we can have a wet layup system, which actually we impregnate the material on site and to be applied immediately. And then we can have pre-cured, which they start looking into developing like sections, I sections and C sections out of FRP. And then we have the pre-preg system, which is less commonly used, but it can be used. The most common used technique, at least in civil engineering or structural engineering, is the externally bonded. So basically we impregnate the material into epoxy and start applying the material to the outside surface of the concrete or the steel. There are some other techniques that are used as well, like the near surface mounted, and that technique, it's a very powerful technique. It just requires some preparation in terms of cutting grooves into the concrete, but you can still embed the FRP in those grooves, and this gives a very high bond strength, and it also protects the FRP from vandalism. Wrapping, which is most commonly used for columns. Reasons to retrofit with FRP, and I like the word retrofit or rehab because it accounts for strengthening and repair at the same time. And there's a difference between strengthening and the repair. Even when we do design, we have to consider, are we strengthening structure, or we are repairing structure, or just rehabilitating structure? And this makes some difference in the design. Yes, we use it a lot for increasing the load carrying capacity of an element. If you have a damage to the structure, which happens a lot to bridges, and we've seen that a lot, impact damage, fire damage, you can use it also for ductility enhancement, and that's mainly for seismic applications when you have a structure that has not been designed under seismic effect, so you need to enhance the ductility of your columns. For blast mitigation as well, seismic upgrade, and also for introducing cutouts or penetrations in your slabs or beams, so you need to do some strength. Durability, yes, the durability, we address the alkalinity of the material, and that's a feature of the glass fiber. We look at the thermal expansion, the conductivity, and that makes the material also ideal when they build hospitals, like MRI rooms, because of the electromagnetic waves. So they start building those structures using carbon bars instead of steel. So what they used to do, they have steel bars and they have to line the entire room with lead to prevent the interference from the electromagnetic waves. So they start using a lot of these carbon bars. And as I said, am I going down? Okay. Now I'll start moving. So this was one aspect, which is the use of the advanced materials. But the idea is not only using an advanced material by itself. You have to have a good understanding of the problem and the engineering itself. So you have to have a good tool that will help you as well. And this good tool that we typically use as a structural engineers or civil engineers in general, we use this a lot. We have to use finite element analysis. But I always like to emphasize that finite element can be a weapon. If you don't know how to use it properly, it could be a problem. At least when I was a young student, when this finite element thing started coming out, like the design softwares, like SAP and other softwares, we were always told a statement, garbage in, garbage out. And I always state to the engineers, if you cannot estimate the results, plus or minus 50%, don't do a model. Plus or minus 50%. I'm not talking about 10%, even 50. So you have to be aware of what you're doing. So when you get to complex structures, we have to start using advanced tools, but we have to know exactly what we are doing. So we start to use a lot of, in civil engineering application, we mostly use the finite element analysis. And this is one of the numerical methods. It's the most widely used, but there are other methods as well, like the boundary method, applied element method. Those are other numerical methods that's used for modeling. However, the finite element, it is still the most widely used one in civil engineering application. A lot of times we have to start relying on nonlinearities in terms of geometrical nonlinearities or material nonlinearities. When we do our models, we use all types of elements depending on the complexity of the problem. What are we modeling? What are we trying to look at? And also the boundary condition. I always emphasize the boundary condition because this is one of the real issues, that if you don't have an understanding what you are modeling, this boundary condition can take you right or left, and you can base your decisions if you're using the wrong boundary conditions based on an invalid assumption. One of the other things, we sometimes look into soil structure interaction. That's also one of the important features. I know in the past, when I was doing my graduate studies, my advisor used to use this very nice, he will have part of the slide as a structural engineers who have a very complex model for a structure, and then we put hinges or fixation at the bottom. And if you go and talk to the geotechnical people, they will have an infinite model for the soil, and they will have a lump mass with a stick, and this is how we represent the structure. But the interaction between the two, believe me, makes a big difference. Try to model a bridge like this one, and include the piles in your models and represent the soil. You will see a lot of your flexibility in the system. You design this column to resist a moment of 1,000. If you model the piles and the columns, you will see this moment can drop significantly. But this is taken as flexibility into the system. So there are some aspects, sometimes it has significant impact. Again, it depends on the problem itself. Sometimes it may not be as complex as it seems to be, but we have to look into all this when we have to make decisions for extending a lifespan of a structure, or we are increasing a load on an existing structure. Just to give you an idea, this model, we were looking into what is the point of fixity of those piles to determine the buckling length, and this was a critical decision to be made if we need to have tie beams to connect those columns at the ground level to prevent the buckling of the columns, but based on the soil structure interaction, we did not end up doing that. Other parameter, we have to look into the damage assessment. You need to have a very careful assessment of what kind of damage you are experiencing in your structure, and you have to account for this type of damages. If you have a section loss, is it cracking? If you have lost pre-stressing strands, so when you model your beam, you have to account for that. So you have to look carefully at the damage assessment and assess the damage and make sure that it is accounted for in your analysis. Is the finite element as a tool by itself is sufficient to stand alone? Sure. However, when we are looking into real life problems and you are making significant decisions, it is easy to look at the model and say, yeah, increase the column capacity at this or that. But when you go on the structure and you have a feeling, it's not an easy decision. So yes, we have to validate the finite element model. And that is not something that could be easily done, but it has to be done sometimes. Especially we have to differentiate between we are doing a design from the beginning. So you can model whatever you want and make a decision. You are designing, you can add whatever layers of safety you want to. But when you are assessing an existing structures and making a decision of increasing the load going on this structure, you have to be sure that you are making the right decision. So yes, we have to validate our models. And the beauty also of validating this model, sometimes you can use the same model if you have similar structures. Now you can use the same model for the same structures. You can also use the same thing to assess any future damage that could happen to that structure. And you can use it for putting heavier loads